I know the density equals mass over volume, which means the mass equals rho times volume, rho, not P, rho, rho times volume. I'll make it look like rho again. It's looking like a P there. My P's and rho's really similar. I know, me personally, I know which one's which. Rho times volume. So the mass of the water here, or the weight of the water, equals mass times gravity. And since mass equals rho times volume times gravity, and the volume is equal to area times height times gravity. So the pressure due to water alone, just to the water, is equal to the weight, the force, which is rho times A times H times G divided by the area. And the A's will cancel each other out. You end up with the pressure being rho times gravity times height. So if you're looking for the pressure at the bottom of that tank, how much pressure at the bottom of the tank is whatever the pressure on the top, the surface, which is P atmosphere, add to it the weight of the water pushing down, which is rho gravity times height. And that's the equation that you see in all these books. Let's take an example here. I'll take a couple examples actually. Let's look at this one. You decide to go and, swimming, or you're down the bottom. This is water, and there's you in the water there. The bottom of the pool. How deep is the pool? 8 feet deep on the bottom? In-ground pool, 8 feet deep. What is the pressure on you on the bottom of that pool? We know on the top of the pool, the atmosphere pressure is pushing on it, on that water. It's constantly pushing down. But on you now, you get that atmosphere pressure. In addition to that, the weight of the water. So the pressure at 8 feet deep, and by the way, 8 feet is roughly what? A foot is almost 30 centimeters. So that's what? Approximately 240 centimeters or 2.4 meters. So what is the pressure on you? It's going to be P atmosphere plus rho times gravity times height. Atmosphere pressure 1.01 times 10 to the fifth. Rho for water, fresh water is roughly 1,000. Gravity is 9.8. The height, which is what? 2.4 meters. Add to it, so this is 1.01 times 10 to the fifth. Add to it the result of this, which is 23520. And the result is 1.25 times 10 to the power of 5. Now imagine if you decide, you know what, I'm going to go into the ocean now, and I'm going to try to go 100 meters deep. 100 meters. Rho for salty water, a little bit different, it's about 1,030, ocean. So rho for that is 1,030. What is the pressure on you now? You're in the bottom of the ocean, right here. It's going to be P atmosphere plus rho times gravity times height. Atmosphere 1.01 times 10 to the 5th plus rho, which is what? 1030. Gravity is what? 9.8. And now you are 100 meters deep. Times 1030 times 9.8 times 100. Ready for this number? 1009400. Add to it 1.01 times 10 to the 5th. It's equal 1110400. Which is 1.11 times 10 to what power? 6. How many atmosphere pressure on you? What is that number if you convert that to atmosphere pressure? 1 P atmosphere is equal to 1.01 times 10 to the 5th. So if you divide this number by this, I'll tell you how many atmosphere pressure. Times the atmosphere pressure. 11 times. 100 meters deep. That pressure on your eardrum, your body, is unbearable almost. That's probably the maximum depth a lot of people will go. 100 meters. That's pushing it. Now the next question, if we have a piece of wood floating, so somehow this piece of wood was floating in the water here. Good chunk piece of wood here. Let's use here 20 centimeters. It's the height of it. I don't care about the length of it. And I'm looking for the difference in pressure between pressure on the top here and the pressure on the bottom, P2 here. What's the difference? Remember, the pressure of P2 here going up, the same from this end, the same from this end, the same from this end. That pressure is the same. What is the difference between them? What I want to know, I can calculate that. You know what? Let's assume this made out of what? Pick something. Floating here. If it's just wood, it won't float like this. It'll be on the top there. But we had a piece of metal on top of it, so it's floating there, or some animal sitting on top of it. So let's assume something kept it floating. It has to be something, because wood will float. It will not. If it's just metal, it will sink. So something kept it actually from sinking. Something kept it from going up there too. So but it was floating there. Could be some people pulling in this direction or that direction. What I'm looking for, the difference between P2 minus P1. It's in the ocean. Rho for water is 1,030. And I didn't tell you how deep is it in the water there. So it could be any depth there. This depth here will be what then? Isn't that D plus 0.2, 20 centimeters? That's a 0.2. I don't know if you can see the point. Can you see the 0.2 there? Yeah. That's the depth of that bottom part. And I'm looking for the difference in P2 and P1. And again, there is atmospheric pressure pushing on the ocean there. It's in the ocean. And let's assume this made out of wood, because I need to know what rho for wood here. Rho W. So for wood here, it's a piece of wood. What is that chart here? What kind of wood? You want to use cherry wood? We have cherry wood. Cherry wood is 800. That's what I'm saying. If it's just wood, it will float on the surface. It will never go down. Maybe a portion of it will go down. But cherry wood is 800? Again, it could be a piece of metal was sitting on top of that to keep it floating like that. So now, what is P1? Pressure 1, that's the top. It's P atmosphere plus the water here pushing on it, which is rho of the water times the gravity times the height of the water. P atmosphere, 1,030 times gravity 9.8 times the height, which is what? D. What's the pressure at point 2? Same thing. At point 2 is going to be P atmosphere, the air pushing down. This water pushing down on a 2. And don't forget to add the wood itself here. The wood has some weight. That's wood. Because I forgot I used W for water. This is wood. The block itself. The block of wood. So the bottom pressure is going to be P atmosphere plus 1030 times gravity, which is 9.8, times the height, which is D, plus the pressure rho for wood, which is 800, times gravity, which is 9.8, times the wood here, the height of the wood, which is 0.2. So when you try to do P2 minus P1, what's going to happen to the first two values here? They will cancel each other out. Notice these two here are the same. See them? So when you subtract them, you're going to end up with P at this one minus P at plus 1030 times 9.8 times D. And you can see that this one cancels that one, this one cancels that one, and the difference in pressure between the top and the bottom will be rho for that substance, which is, or material, which is wood, times the gravity, which is 9.8, times the height, which is 0.2. And that's the difference in pressure right there. $15.68. Here's the one thing to remember about fluid there, water or oil, whatever the case is. If we have a shape, and we can do this in the lab, we have the bottom looks like this with some openings in it. You have a tube that looks like this on the top. This one is a skinny one that looks straight up there. This one, it looks like this with the bubble here. Then here, another bubble. This one is a big tube that goes on angle. And if you pour stuff on it, if you pour some oil or water inside that container there, you're going to see the water. It'll say blood we're putting there. Could the picture look like this? The answer is no. Why? They're all going to reach the same height. So you draw the line that's height like this, and if you look at all of them, the height of the water or the blood, whatever you use in there, will be the same level. Doesn't matter what the shape looks like. Doesn't matter how wide, how small. Doesn't matter if there's a bend in it or not. All four of them will reach the same height. They have to. Why? Because the pressure has to be the same. If they have different height, they have different pressure. So the pressure will push them down, and you have different pressure. Now we decided to use our logic for this example. The topic, it says water and oil don't mix. I was about to say we decided to use this logic for car lift, when you make a car lift, which is the same thing. You'll see that in a minute there. But let's take now a different example here. And the example I'm going to throw is I have a container that looks like this. And you had water in it up to this level. Let's say that's water. But now you decide to put some oil in it. Oil has less density. So we added some more oil to this on one end after you put the water. We'll put some oil here. And it went this level. What's going to happen, this water will push down on this, and this end will rise. It will not be the same height. So the example here, we have a U-shaped tube. That's what we have, filled mostly with water. A small amount of vegetable oil, that's the red one, was added to one side. The density of water, there we go, rho for water is 1,000. Rho for vegetable oil, rho for oil, is 920 kilogram per meter squared. if the depth of the oil is 5 centimeters, this is 5 centimeters, 0.05 meters. What is the difference in the level H? That's the height. This is H. H is this distance right there. What is H? Okay, so find H. That's what the question is. Let me draw a line from the edge of the water here. This water started right here. Let's call this point P1, pressure at point 1, and this is pressure at point 2. Since these two pieces are the same levels, that's full with water, the pressure on them has to be equal. It has to be. Same height, same pressure. Always. So P1 here, the pressure at point 1, has to equal the pressure at point 2. Well, what is the pressure at point 1? First, we got the atmospheric pressure pushing down, plus what? The weight of the water. So rho for the water times gravity times the height of the water. And my next question for you, how high the water? What's the height from here to here? We'll come back to it in a minute there. Point 2 here, we have the atmospheric pressure here, pushing down, plus rho for the oil, times gravity times the height of the oil. You can see mathematically, P atmosphere will cancel each other out. It's on both sides of the equation. If I move them to one side, you're subtracting the same thing. They cancel out. So what's left is rho for water, which is what? 1,000. Gravity of water, gravity, which is what? 9.8 times the height of the water. What is the height of the water? What is the distance from here to here? What do you think? Okay, let's leave it, we'll come back to it. What is rho for oil here? 920 times gravity 9.8. What is the height of the water from here to there? 0.05, good. So the only thing holding me back is this one. Let me go back to this one, see if I can figure that. Can you tell me what the height from here to there is? What that height is?
Is it half of 0.05?
Well, it's not, because we're not sure what h is. Think again. Isn't that this distance from here to here minus this distance? So what is it? 0.05 minus h. The whole thing from here to there is 0.05. This is h, the difference between them. So let me put that here. How many unknowns do you see there now? Just one. Can we figure out what the height is? A 1,000 times 9.8, that's 9,800 times 0.05, distribute that, 490 minus 9,800 H equals 920 times 9.8 times 0.05, 450.8. Take this one to that side. $450 minus $490. That's negative 39.2. Can we get what H is? .004 meters, which is what? 0.4 centimeter. So the height, H, the difference between this end and that end is only going to be 0.4 centimeters. Excuse me. One more example on these shapes, then we're done for the night, or the day, the afternoon, whatever it is. Same shape here, but watch what happens when you take your car to the mechanics to work on it. As you know, I want to change the oil. They take the car, put on a lift, raise it, unless you go to Jiffy Lube, they don't lift them. But normally they put them on a lift, and that lift will raise the car. So you have a design that looks like this. And you got the car sitting here on a lift there. There's your car. Up there. On this end, they just apply a little pressure and you see that car goes up there. What happens actually with that lift, they apply a little force on the top here. They come in, they apply a force to push down. And it's going to push, there's actually fluid inside this. This is filled with fluid. So this height is the same for both. I'll just draw a line here. Initially, then the push down, what will happen, this will go down probably this much. Now this is empty here. You pushed it down. And this one goes up a little bit higher and lifts the car up there. That's what's going to happen. Initially, they were the same height. They push down, you push down on this, the car rides on that end. The distance this one traveled called D2, this distance is D, or D1 here, D2 here, we'll call that 1 and 2. That's what happens usually with your car. By the way, a couple of times when I wrote the unit for pressure, I wanted to write PA which is the correct term for pressure. PA. Anyone knows why PA is not P atmosphere? Pascal did a lot of work on pressure, and we use the term PA for Pascal instead of kilogram per meter squared. PA. So if you see me write PA, that's for Pascal. You know. Actually, Pascal came up with this. Again, I'm still going to use the pressure equals P atmosphere plus rho times gravity times height. Now, let's pick what will happen actually here. You'll see the equation math. Pressure is force over area. Notice what they did in the design. They made this area really what? Small, the cross section, and that area much, much bigger. Since pressure is equal force over area, that's P for pressure, not rho, pressure. So you're going to find the relationship between the pressure here, the force, pressure 1, it's force 1 over the area. The area is what? Pi r squared. And with the design of these, they made this r really small. Let's use, for example, I don't know, r equals 1 centimeter, small 2. So it's going to be F1 over pi times 0.01, I'm sorry, 0.01 squared. On the other side, pressure 2, if you pick the same height, pressure 2 is going to be what? Force 2 divided by area 2. Well, force 2 usually is the weight of the car, which is mass times gravity, or the weight of the car. And area 2 is what? That cylinder usually is a good sized cylinder, probably has 15 centimeter radius. Over pi r squared. It's F2 over pi times r, which is 0.15 squared. And if you pick a spot like this, the height is the same, that means the pressure is the same. Well, if the pressure is the same, set these two equal to each other, what are you going to have? Force 1 over pi r1 squared, as I'm trying to come up with an equation, equals force 2 over pi r2 squared. This is r sub 1, this is r sub 2. Crisscross, F1 equals pi r2 squared over pi r1 squared times F2. You can find the relationship between force 1 and force 2. Or if you want force 1 over force 2, that's this one over that. Again, if I use these numbers, that's 1 centimeter, 15 centimeters. We can get the relationship of force 1 versus force 2. How much forces? And if you want the pressure, pressure is force over area. So you can convert the ratio of pressure if you want. And if your car is the big car, Should be R1 on the top, right? Cross multiply. Force 1. This is R1 squared over R2 squared. Yep, cross multiply them. Cross multiply. This goes with this goes with that, then you divide. Sometimes try to cut corners, but I have F1 pi R2 squared equals F2 pi R1 squared. And if you divide both sides by this one, you end up with that equation. So force 1 will have to be much, much smaller than force 2. So just to give you an idea, if the car weighs, let's say 2,300 pounds, force 1 will have to be 0.01 squared over 0.15 squared times, let's say the car is 2,200 pounds. You only need about less than 10 pounds of pressure to lift that car. 10 pounds of pressure. So you can take your hand, push down on that cylinder. If it's cylinder, push down, lift that car up there. 10 pounds. That's why when you look at the bulldozers, look at the lift on the bulldozers. Look how small the tubes on them. The hydraulic tubes, very, very small, the size of this pin. The smaller that value there, it lowers the ratio because pressure is force over area. So when that becomes small, the area is small, that actually the pressure becomes really large there. Just got to make sure that tube doesn't burst. The force is not large, but the pressure will be large. So if you can maintain or design something where the tube is not going to burst, then you don't have to push that hard to lift anything. 10 pounds will lift a car that's 2,200 pounds. So you can take your baby, put them on top of it, and you'll see that car goes up there. 10-pound baby, newborn baby. Little chunky one, 10 pounds. But that will lift that car up there.